trip to go and look at how we recover all the things that we design. And this is actually a shot from an e-waste recycling centre in Dagenham. This guy here was taking apart an old television. And I was standing behind him watching this guy having to use such a lot of strength and a massive hammer to basically smash out all of the bits inside this television. Quite an old-fashioned one, you know, the big box ones. In fact, we have 3 repaired ones on our stand there, and they're called cathode ray tube televisions, CRT televisions. They've got this massive glass vacuumed globe in the middle. And the reason why he's trying to get that out is because inside that is a covering of lead. And I don't know if you've ever seen some of the films about children in Africa and India burning, trying to get the lead out of this glass. It's so horrific. It's very, very toxic. In Dagenham, they can get 1 kilo of lead out of each television, out of this glass. And 1 kilo of lead at today's prices is very, very valuable. I will show this picture because a friend of mine who's got this amazing telescope in his garden took this picture. And this is actually of a star nursery called the Elephant's Trunk. And the reason why I show this to designers and to people is I say, look, this is actually where all of the stuff that is all around us comes from. Every single element in our solar system, in our universe, comes from star nurseries. They're born in stars. Even us, you know, you've heard the phrase, we're all made of stardust. And there are 94 very, very useful elements in our periodic table. And all of those elements, particularly 94 of them that are very useful, make the stuff that surrounds us. All of this stuff comes from that star nursery, right from the beginning. That stuff takes billions and billions of years to make. And yet here we are, making new things, producing new things, getting it out into the shops, getting people interested in it, thinking about promoting it, getting people to buy it, getting them to use it. Then actually, what happens to it after us? This man tries to have to take it apart physically, or we throw it away in landfill. If you take something like a mobile phone, you can start separating out all the different elements that sit in that mobile phone. So in this particular mobile phone, there are 40 elements, 40 out of 94. And currently, when I finish with this mobile phone, I might, if I can, send it for recovery, send it to a recycler. And if they want to actually get the stuff out of it, they probably only get about 5, I think. They probably get gold, copper, zinc, and nickel, and probably the plastics. So all the rest of those, all the other kind of 35, get put into incinerators and get burnt away. With the Great Recovery, we're trying to get designers to think about what's the ingredients list. Do you understand your materials enough? Do you know how people are going to be able to take it apart eventually? You would think that we're quite good at recycling. You think that we have good systems. But actually, we're pretty linear. We have 81% of our materials coming in and going out again. We're only actually recovering 19% or so. The rest of it is going into embedded things. It's going into recovery. It's just going out of the system. Why is that an issue? Last year, 1/3 of the profit warnings from manufacturing and from companies was duly responsible because of the increase in resource cost. So actually, business models now are built on systems which probably can't survive in the next 5 to 10, 15 years because our resource prices are going up and up and up. Copper last year hit an all-time high of $10,000 a tonne. And if you look at the chart of how expensive copper has become over that period, it's sort of going like this, and it's suddenly it's peaking really, really high. We've got hitting this point where we're actually using more than we're getting out of the ground. It's the same thing that's happening in a lot of our elements. So, for instance, indium. Now, indium's a very interesting element because indium is the conductive, see-through, transparent layer here on your touchscreens and on your iPads. It's a very, very useful material, and it's really, really important for third-generation photovoltaics because we need it to get all the energy in. The problem now is that we don't actually have proper recovery facilities in the UK for indium. We're not designing these kind of things to get that indium back out again. So our proposition about this is really that this is a design issue. The fact we're designing things that we can't take them apart, we can't get the elements back out again. We're being very good at creating objects that are desirable, objects that are very efficient, objects that, or things around us that work very well, but actually we're not thinking about the end of that. We're not thinking about the end process. How do we get it back again so we can redesign things in the future? And I want to take a really, really simple example to talk about this, and that is the toothbrush. It's very disposable. It's very cheap. The design brief for a toothbrush is about getting the plaque off your teeth, being comfortable to use, has to be the right price point. often as a consumer, you're faced with this huge wall of toothbrushes. How do you choose the toothbrush? I choose the toothbrush usually on a brand that I used before, price again, and sensitivity or something like that. I never ever choose a toothbrush. Even though I've been interested in these kind of things for over 16 years, I never choose my toothbrush based on sustainability. Why would I? I just want to brush my teeth. I expect the people who've designed that toothbrush to maybe have thought about it, but maybe not. This toothbrush, if we look at like what's gone in terms of the raw materials into the toothbrush, actually weighs about 1.5 kilos of raw materials. That's in the plastics alone and the transportation and all the other things that I've taken into account to get that toothbrush to me. This toothbrush is actually, just looks like a disposable plastic toothbrush. This toothbrush cost me probably about £2. It had on the back of the packet, it tells me that I have to use this toothbrush for the recommended time of about 3 months. That means that I probably go through quite a lot of toothbrushes. Because of the way it's designed, it actually has squidgy bits, nylon-y bits, plasticky bits. There are actually 4 different types of plastics in this toothbrush. We've got high-density polystyrene here. We've got high-resistant Kraton, which is a new rubber technology. The interesting thing about Kraton is that it's a natural rubber alternative, and it's got incredible resistance to heat, weathering, and chemicals, which is exactly what you need for a toothbrush. What's interesting about the way this toothbrush is designed, it's molded as one. So all of these plastics came together and were pressed together in this mold, which was absolutely revolutionary at the time when it was designed. It was seen as this great design shift. But the designer didn't really think about what happens to that toothbrush when I throw it away. Because we can't split the plastics and the way it's molded, I can't actually recycle it because these plastics can't go into the same recycling stream. So this toothbrush is destined, by the way that it's designed, into a landfill. And actually that becomes a small little toothbrush. You don't think that would have much of an impact. The US landfill 25,000 tons of these types of toothbrushes a year. If you start to build up the picture of all of the stuff that we are consuming, it becomes incredibly frightening and really ridiculous. So I was on a beach, I was having a fantastic holiday, and lo and behold, I found my toothbrush on the beach. Here it is. This is my toothbrush. Well, it's not exactly my toothbrush. This toothbrush has actually probably been in the sea for a couple of years. And you can see that it's actually, if you really were quite desperate, you could probably still use it. It's had very little use. So I started thinking about this and thinking, actually, this is crazy. You know, we're creating this stuff, and it's just not going to disappear because of the way we've designed it. Then, if you think about the different types of toothbrushes you come across, this is actually a disposable electric toothbrush, which is even more ridiculous, because actually if you look on the back of that toothbrush pack, it tells you that you don't need to charge it. It's got a battery in it. Also lasts for 3 or 4 months. Please change your toothbrush every 3 months. You're supposed to recycle this toothbrush. In fact, it has the redirective sign on it here that tells you can't throw it away, you have to recycle it. My husband had this toothbrush. I tried to put it in the recycling bin. They wouldn't take the toothbrush. They don't recycle toothbrushes. They don't know what to do with it. So I decided to take it apart. You're not actually supposed to take it apart. It does tell you not to take it apart on the packet. This is where the battery sits here. I had to get my toolkit out, take it apart. First thing I found out was actually, although it's an electric toothbrush, if you take the head off, the electrics doesn't actually attach to the head. All it does, it just makes your hand vibrate. And actually it has these little wiggly bits on it that makes the things vibrate a little bit too. So it's actually not an electric toothbrush, just feels like one. But we took it to one of our material scientists and said, can you tell us what's in this toothbrush? And he came back with this list. Effectively, exactly the same elements that are in this are in that electric toothbrush to a smaller degree, including things like tungsten. He was like, why the hell is tungsten in this toothbrush? Neodymium is another very interesting element on our periodic table. Again, it's one of the rare earths. It sits in a critical element list that the EE brought out a couple of years ago. Neodymium is used in motors, and we need it for all of our big wind turbines and for creating renewable energy. But yet we throw away a lot of it in our motors. And a report that came out a few years back, the Design Council, said that 80% of the environmental impact of products is predetermined at the design stage. So a lot of the stuff that we don't yet process plastic particularly, ends up floating in the sea. And this used to be a pristine beach. And this is on the edge of one of the Pacific garbage patches. And when they have big storms, all of this flotsam and confetti just ends up. And they have to dig a metre down to find the sand again from this stuff. So this is an albatross chick who's been fed plastic by the mother, because they see it, they think it's jellyfish, they think it's nutritious, and they end up kind of trying to fly. They have a belly full of plastic bottles and lighters and toothbrushes. Plastic basically doesn't biodegrade. It doesn't degrade by sun. In this particular area of the garbage patch, you've got 6 more pieces of plastic to plankton, and it's starting to affect food chains. So as a designer, what I want to see is all of these things come together. So I really sit here, but actually I can't do it on my own. I know that I have to have informed customers to start thinking about how can I change the way that we start building accreditation and certification for design communities, and also we need EU regulation. And all of this comes together to create things that actually can be quite responsible. As a designer, how I was taught to design was very linear. I got a brief from the client, and I worked on a product, and I looked at production and consumption, but not really. That's as far as it kind of went. I basically had this very, very linear process of design. What we need to start doing is bringing in those 2 areas. So what goes into my product and what's going to come out of how am I going to get it back out again, and create this kind of cyclical process. It goes from the stuff we take out of the earth, we make it into products, we consume it, and then what do we do with it? We find different ways of disposing in it. What we don't want it to do is to go into the waste, into the landfill. What we're trying to look at is the different circular systems. So this is the outer ring. So we want to at least recover the materials that goes into our products. We also want to talk about remanufacture. We don't necessarily have to completely deconstruct something. It could be just upgraded and remade again. And then we talk about fixing. As a consumer, maybe I could fix it. Maybe I could repair it myself. So design is about either disassembly, either remanufacturing, looking at new service design and how we can enable people to fix their own products, and designing for longevity. And these are quite separate ways of designing things, but actually they all sit in the same kind of circular system. The Great Recovery is a 2-year program. If you're a designer, if you're a chemist, if you're a material scientist, if you're a technologist, if you're a business, if you do brand licensing, if you do policy making, we want to get everyone together into the room to start discussing some of these issues. We want to start looking at the end of life of things as they currently stand and moving away from that. Get that linear process of design back into a loop, whether it's about paper, whether it's about domestic objects, mattresses, terrible things, have 18 different layers of ingredients in a mattress. So we can actually start saying, this used to be a fridge. This was how we should be thinking about things, how we can break those down. This company in the Netherlands could take fridges and absolutely take everything out of it, even the gas that came out of it, they would suck out, and you could take it and they completely made them again, back to their base equipment. This is our current network wheel, so we hope that you are all on that wheel somewhere. And what we're trying to do is to say, all of these people need to connect to this person or this person, and we can help broker those conversations with the Great Recovery. And then we're hoping for new collaborations to come out of it. Perhaps there's somebody there who we can link you with who's looking at new textile technology and chemistry. Perhaps there's somebody there who's working on a new policy about accreditation for furniture, flame retardancy. We need to get all those people together so we can actually look at the systems that are currently set up and how we can redo them, but in a very innovative and creative way, because creativity is the one thing that will really shift all of these arguments.